Okay, so I was doing a problem to calculate the temperature in last class, so we stopped there. So I just show it here now. So this is a slide number 10 that I left last time. So what it is saying is, I mean slide number 10, slide 10 from last class lecture. So I have some gold here. So this is gold pieces. These are gold. And the gold mass of the gold is given as 182 grams. So the mass M1 of this one is given as 182 gram. And and we have some water here. So this is water. So two things, we are mixing two things. So water is added to 22.1 gram of water. So the mass of this water is 22.1 gram. The temperature of the water is given as T1 is 25 degrees centigrade at the beginning, and the final temperature of the resulting mixture is 27.5. So the gold temperature here is not given, so that this T1 is not, what is the T not given. So what they did is, so this is the gold at certain temperature, and they throw this gold to this water and measure the temperature here, right? So that's what they are doing. Make sense? So they don't give that temperature, and after mixing, when they mix these two together, the T2 here is a water as well as the gold. So the T2, the mixture of the the temperature of this mixture is how much they give is a 27.5 degrees centigrade, just like that, yeah. And the specific capacity of gold is given as C1 is equals to 0.129 joule per gram per degree centigrade. And the specific capacity of this one, let's say C2, is always 4.18 joule per gram per degree centigrade, because that's the water, right? Now, so this, when we mix this gold to this water, the temperature of this gold is going to go down, the temperature of water is going to go up, right? Because this is hot, this is cold. So one is losing heat, another is gaining heat. Suppose that this is losing heat, so I would give the minus sign this one. So it loses minus Q amount of the heat when I mix this to here, right? And then this water is going to get how much heat this lost, that much heat it is going to get. Like this. When I need to calculate the temperature, I need to put a minus sign in one side. Yeah? But if I were calculating the specific heat capacity, I would not put minus sign. I just put a plus both sides, and then I would calculate the M and or C I need, and if minus sign comes there, I say, oh, mass cannot be negative, so I just disregard. C cannot be negative, I disregard. But if there is a temperature need to be calculated, I need to be careful. Always, if you have to calculate temperature, always put minus in one side. So either you can put minus this side or you can put minus this side, is the same thing. It gives the same result, yeah? But normally, something that lost the heat is given as minus, something that gained the heat is given as plus. Now, put the values here. So minus here, so how much heat it lost? So M1 is 180. So Q is given by this equation, right? Always M C T2 minus T1. So this is the equation. So minus M. So M1 is 182, C1 is 0.129, and this is T2 minus the T1. So after mixing, that's a T2. This is 27.5. So this is 27.5, and T1, I don't know how much T1 was here. That's T1. That's the left side. Make sense? So I already wrote here. So now this side. So that's the gold side. Now I write this to the water side. So I have a plus here. Again, M is 22. I don't need to write the plus here because this plus is even if you write or don't write, it's the same thing. 22.1. That's M2. Now C for water is 4.18. And then T2 minus the T1. So T2 was 27.5 after mixing, and then T1 is 25. Now you have everything. So everything is here. Now you just need to calculate this T1, right? So put this number and this number in calculator, and put this all number in calculator. You get one number here. You get one number here. So left side you will get minus 27. So in left side, when you solve this equation, you will get minus. There is a first, second, third. In fourth line, I put two minuses there. That's not two minuses. Only one minus there. Yeah. So that's a mistake. So in the fourth line, you will see minus, minus. That's not two minuses. That's only one minus. That's minus 27.5. When is the next exam? So next exam is the first of next month. So April 1. So 27.5 plus the T1 plus the T1 is equals to 9.83. So you can just solve that equation there, yeah? So what I did is, so I put this number in calculator. So maybe I just calculate this one and I put this number down here, and when this factor remains here, so this gives this one. Now T1 equals to, take this number this way. That gives you, so T1 is equals to 9.83 plus 27.5. It gives you 37.3. Make sense? So try solving that equation. So what I did is, so multiply this one, subtract this one, multiply, multiply, multiply here. You multiply this by this, and then divide here, and you get 27.5 here. By multiplying this minus, minus comes here, and minus minus becomes plus here, and this gives, yeah. So that's how we solve. So try solving that equation, and you will get that. So if you have to calculate mass or specific capacity, no need to put minus or plus. Alrighty, so now I finished this lecture. Two slides that I posted there. Now I teach another set of the slide. Yeah. So this is about the energy and changes of state. So these are new slides. The third lecture in Canvas. So so first of all, heat of fusion. Heat of fusion. Heat of fusion. So what is fusion? Fusion is melting, right? If you take ice and heat it, the ice melts. That's called fusion. If you take some piece of copper and heat very high temperature and copper melts, that's called fusion. So anything solid, you start to heat and it melts, it's called fusion. Yeah. So what is heat of fusion? So heat of is required to convert solid its melting point to liquid at melting point. So let's say you have ice here. So this is ice. It's ice here. Put thermometer here. Put thermometer here. It will show 0 degrees centigrade because ice has a 0 degrees centigrade temperature, right? Now give heat to this one. Heat it, and then it completely melts and becomes water. Now it's a liquid water. Liquid water. And still the thermometer is there, and it's still showing the 0 degrees centigrade here. So how much heat it absorbs is called the heat of fusion. Make sense? So both sides, here also 0 degrees centigrade, here also 0 degrees centigrade. But this is ice or solid, this is liquid. So how much heat is absorbed by a gram or a kg of ice to convert from solid to liquid, and both has 0 degrees centigrade. That amount of heat is called heat of fusion. Make sense? The temperature must be the same both sides. So here is a solid, this is liquid. So solid, we heated the solid at 0 degrees centigrade to convert to liquid, and the temperature is still 0 degrees centigrade here. And that amount of heat is called heat of fusion. So 1 gram of ice at 0 degrees centigrade is 333 joules of heat energy. So if you take 1 gram ice here, 1 gram ice here, how much heat you should give? It's at 0 degrees centigrade. So 1 gram ice here, this is 1 gram ice, and it's at 0 degrees centigrade. And if you heat by giving 333 joule of heat energy, it just changes into the liquid and temperature is still 0 degrees centigrade. This is liquid. Make sense? So the heat of fusion of ice is 333 joule per gram. So meaning that take 1 gram of ice in the beaker, measure the temperature, that's 0 degrees centigrade, start to heat it, and all the ice just melt and becomes water, and still the temperature here is 0 degrees centigrade. So it absorbs 333 joule of energy for that process. Make sense? Good. Now, another term is heat of vaporization. Heat of vaporization. Heat of vaporization. So again, heat of vaporization meaning that here take 1 gram of water, 1 gram of water at boiling point, 1 gram of liquid water, 1 gram liquid water. Liquid water. Take 1 gram liquid water. What is the temperature of this water? 100 degrees centigrade. So boiling point. The water is boiling there. Yeah. Now, what happens after boiling? It just evaporates, right? It becomes vapor and goes out. Now, when you heat it further, what happens is all that water goes as vapor. All that water goes as vapor, and then the temperature still is 100 degrees centigrade. Make sense? So take liquid water, 1 gram, put in the oven, boil it, and the boiling point is 100 degrees centigrade. Now start to further heat it, and the temperature of water doesn't increase. The water start to become vapor. So it's all vapor, and the temperature is still 100 degrees centigrade. So this is liquid water. Liquid water. This is liquid water at 100 degrees centigrade, and if you further heat it, the temperature does not increase. Temperature doesn't become 101, 102, 103, 105. The temperature of the boiling water doesn't increase, right? So what happens is the water starts to vaporize, and then all converted to vapor. And then if they measure the temperature, it's still 100 degrees centigrade. So how much heat it requires to convert 1 gram of water at 100 degrees centigrade to convert to vapor at 100 degrees centigrade? This is 2256 joule. 2256 joule. A lot of heat energy. So it's pretty easy to melt the ice, but it's very hard to convert liquid water to water vapor at 100 degrees centigrade. Make sense? So you probably heard already in hospital they call, if we are born with the vapor, water vapor, burning is very severe, but the burning by boiling water is not that severe. Why? Because if the burning by boiling water, maybe it gives heat, let's say 1000 joule heat to burn by boiling water, right? But if you are burned by the water vapor plus that much, 2256. So it's given by 32 56 Make sense? So if you have a 1 gram boiling water, you put in your skin. So your burn is not that bad because you just get 1000 joule of heat energy from the boiling water. Yeah. But if you put 1 gram water vapor, that's already at 100 degrees centigrade. That has 2256 plus 1000 would be 3256 joule of heat energy. So the water vapor always has more energy. Make sense? Good. So why the burning by boiling the water vapor is safer than burning by boiling water? Because of this heat of vaporization. So the water vapor takes more heat from the oven, and it's already become too hot. Yeah. Good. So now let's go to the next slide. Slide number 2. So temperature of a substance does not change during the phase change. So let's say you have ice here. You have ice here. Ice. So this is a beaker. I have ice here. and then I put a thermometer here, and the thermometer shows 0 degrees centigrade. 0 degrees centigrade, right? Now I start heating. I put it in the oven and heat it. I heat it, and I keep heating. It, the ice melt and ice melt, and it becomes liquid, but the temperature does not change until it becomes the liquid. Make sense? So the temperature of a phase does not change on heating until this phase is completely not changed. So this is solid phase. Ice is solid phase. So if I start to heat it, temperature never go above 0 until this solid becomes all liquid. So the heat absorbed by that ice is used to melt that ice. It is not used to increase the temperature. Yeah. So now it becomes first you heat it, and then it becomes all liquid. It becomes all liquid, still at 0 degrees centigrade. Still at 0 degrees centigrade. Now heat further. Now if you heat further, now it becomes all liquid. Now if you heat further, the temperature start to increase. Maybe 25, 26 degrees centigrade, 27 degrees centigrade. That works that way. Make sense? So as long as solid is there, no matter how much heat you give, the temperature does not change. Where does the heat you supply go? The heat you supply go to melt that ice, to break those bonds of the ice. Yeah. So as long as the phase is the same phase, the solid, the temperature of this thermometer does not. The temperature of this thing does not go up. Does not change. Now let's look another one. Same thing. Now you have water here. So this is water. This is a liquid phase, right? Liquid phase. Liquid water is liquid phase. And this is boiling. Already it's boiling. So this is 100 degrees centigrade. This is 100 degrees centigrade. The water is boiling here. So keep heating. The water temperature does not go up. 100 always become 100, 100, 100, 100, 100. At a certain point, when all the liquid is gone and becomes vapor, all becomes vapor. Now this is also 100. Now it says the 100 degrees centigrade. The thermometer says 100 degrees centigrade. This is liquid. This is liquid. This is liquid. Yeah, it's liquid. Now this becomes all liquid becomes vapor. Now heat further, and only temperature start to go up. Maybe 110 degrees centigrade, like this. As long as liquid water is there at 110 degrees centigrade, no matter how long you heat, the temperature is not going to change. Where does that heat go when I am heating? The heat goes to change the liquid to vapor, because liquid molecule are attracting each other, and then when I heat it, the heat I supply is used to break those force of attraction between the molecules and the molecules. Make sense? This is an important concept. Yeah. So as long as the liquid is at 100 its boiling point, the temperature doesn't change, no matter how long you heat it. But once all liquid is converted to the vapor, and if you heat further, only then the temperature of the vapor start to increase. Yeah, good. So I already wrote there. You can read that now. 3. And now there are a couple of problems here. So let's do the problem. In the slide number 3. So in slide number 3, the problem is, what is the quantity of heat absorbed by 500 gram of ice is warmed from 0 to liquid water at 0. So you have this is ice. It is at 0 degrees centigrade. So thermometer is here. So this is 0 degrees centigrade. Now you heat it, and it completely becomes water. Now it becomes water, and temperature is still. This is ice. This is ice, and temperature is still 0 degrees centigrade. 0 degrees centigrade. What is the mass given? Mass is 500 gram. So the mass of this is given as 500 gram. So we already wrote that to convert 1 gram water completely to 1 gram into the liquid at 0 degrees centigrade, we need 333 joule of heat energy, right? If you go to the previous slide, you can see that if I take the 1 gram of ice and heat it and completely change to the liquid water at 0 degrees centigrade, I need to supply 333 joule, right, for 1 gram. Now you can easily know if you 1 gram needs 333, 500 gram needs how much? Multiply by 500, right? If 1 gram needs 333, 5 gram would need 333 joule multiplied by 500. 1 gram needs this much, 500 gram needs more, right? Easy. Or you could just use a formula also. You can do like this, or you can use also the formula. The heat of fusion is equals to mass multiplied by Q. Q. So the heat absorbed equals to mass multiplied by heat of fusion. Heat of fusion is of 1 gram, right? Mass I have 500 gram, and then heat of fusion of ice is 333 joule per gram. This is gram. So gram cancel. So 500 multiplied by 300. So you can do either way. So rather than using formula a lot, I like this kind of math actually. If I need just for 1 gram, I need this much heat. For 500 gram, I need to give more heat, right? So I just multiply, yeah? So either way, whatever you want to do, yeah? Good. The same thing, so go to the next problem number 2. What is the quantity of heat absorbed as 500 gram of water at 100 degrees centigrade is converted to water vapor at 100 degrees centigrade? So number 2 is like this. So here, number 2, I have water here. This is water. So I put a thermometer here. It is showing the 100 degrees centigrade, liquid water. So liquid water, right? Now I heat it and then completely convert it to vapor. So this is liquid. This is liquid at 100 degrees centigrade. And I can completely convert it to vapor and measure the temperature, and still I have 100 degrees centigrade here. So this is vapor. And how much mass I have here? The mass is 500 grams. So the mass is 500 grams. Again, same thing. So I already told you in the previous slide, 1 gram of water at 100 degrees centigrade would take 2256 joule, right? A lot. So 2256 joule. If I would take 1 gram here, it would take, if I take 1 gram water here at 100 degrees centigrade, it would take 2256 joule heat energy. But I'm taking 500 gram here, so 500 gram would take a lot of energy. 2256 multiplied by 500. So you can do this way, or you can just apply the formula. Another way is the same thing. This is the number. Another way is Q is equals to heat of vaporization, vaporization multiplied by the heat of vaporization multiplied by the mass. You can also do this one. Heat of vaporization is for water is 2256 joule. Mass is I have 500 joule per gram. So gram here, gram cancel. You can do also this one. It's the same thing. Just multiply, right? 1 gram needs that much. 500 gram would need a lot, right? So we multiply that one. So same thing. So go to the slide number 4. Everything is same, but there is a kilojoule heat. So I give the 6.3. So I'm talking in the slide number 4. So let's do slide number 4. So everything is same. The value of Q is given as 6.30 kilojoule. So kilojoule. So convert that to joule. So 1 kilojoule is equals to 1000 joule. 1000 joule. So this is the conversion factor, right? Kilo means 1000, right? 1000 joule. So I don't need this kilojoule. So I convert this into kilojoule. So I put this factor to cancel kilojoule. So 1 kilojoule I put this way, 1000 joule this way. Now kilojoule cancel. I would put this number in calculator, and this gives me 6300 joule. So do the same thing. So Q is given, mass is given. Let's calculate the heat of fusion. Same thing. So That's heat of fusion is equal. So Q is equals to heat of fusion, heat of fusion, heat of fusion, right? Fusion. Heat of fusion, fusion multiplied by the mass. Same thing. So put the value of Q, that much it absorbs, and put the value of mass 255 here, this number here, and then calculate the heat of fusion. Yeah, just put in calculator, and you can easily calculate those. Now, this slide is really important. So number 5, slide number 5 is really important. So I'm going to work here. So in homework, this slide number 5 is in homework. Yeah. So this one. So first law of thermodynamics. I already told you first law of thermodynamics is first law, FIRST, first law of thermodynamics. First law of thermodynamics. So this is very important slide, very simple but very important. So it's the same thing. Energy cannot be created, energy cannot be destroyed, but it can be changed from one form to another, right? So I told you at the very beginning. So first law of thermodynamics says we cannot create energy, we cannot destroy energy, but energy, one form of energy can be converted to another form of energy. So this is called first law of thermodynamics. So the definition is already there, you can read it. I just show the mathematical form of this equation. So let's say you have a gas here, some gas here. It's a gas here, and you have a piston here, just like the car. So this is a piston. So this is a gas, and you have a piston here, right? Make sense? Now I heat this gas. I heat this gas by supplying, let's say, Q joule of energy. Q joule. I give Q joule of energy to this gas, right? Now two things happen. What happens? This gas, this piston is going to move up, and I have also a thermometer here. I have thermometer here. So what happens when I heat it by putting in oven? So what happens is like this. So this piston is going to move up like this. Piston move up like that. Yeah, make sense? And the thermometer is still there. So let's say at the beginning, this thermometer was showing 50 degrees centigrade, and after a while, the thermometer may show you 80 degrees centigrade, something like this, because I am heating, right? So what happened here? So I put some gas here, and there is a movable piston. When I heat it, the gas is pushing this piston up, and the temperature of the gas is also increasing, right? So two things is happening here. So the heat I supplied did two things. The heat I supplied did two things. One thing, it moved the piston up, so that we call work. Work. dW is a small amount of work, yeah? So you could write the dQ here also. D means very small amount. dQ means, Q means heat, dQ means very small amount, yeah? So that D shows very small amount. Make sense? So dQ. So I supply some amount of heat here. What happened? So this gas moved this piston up. So by how much energy this piston moved up is given by dW. That's the energy used to move the piston up. Yeah. And then where does the another part of the heat go? Here was a 50 degrees centigrade. There is a 80 degrees centigrade. The another part of heat goes to increase the temperature. So this is given by internal energy. So this is related to temperature change. So if you put the piston in the oven, what happens? It absorbs some amount of heat, Q. And what does that heat divided into? Some amount of the heat push the piston up, and some amount of heat change the temperature of the gas. Make sense? So they are equal. So let's put a number here. Now I'm going to do So I just do the one problem here, and so let's say I take out this one and like this. So let's say I put 100 joule of heat energy. I put this in oven and it absorbs 100 joule, right? Now let's say to push this piston up, let's say it uses 30 joule of heat energy. 30 joule of heat energy to push this piston up. So how much heat energy is used to increase the temperature. So I need to calculate that one, right? So the first law of thermodynamics said dq is equals to du plus dw. So how much heat energy it absorbs? 100 joule, right? So dq is 100 joule. It absorbs 100 joule. And how much heat energy it used to push the piston up? 30 joule. So 30 joule. This is 30 joule. Now, how much heat energy it used to increase the temperature from 50 to 80? So du. So I don't know du. So I want to calculate that one. Make sense? Now I take this number this way. 100 minus 30 is equals to du. So 70 du. So 70 joule of heat energy. So out of 100 joule, so I supply the 100 joule of heat energy here. Out of that 100 joule, only 30 joule of energy is used to push the piston. That's a word. That's a good thing. But a lot of heat, 70 joule of heat energy is just used to increase the temperature, which is not good. So D in thermodynamics, du is not good. dw is always good. So driving a car, when you are driving a car, you start a car, your engine becomes very hot. That's very bad. Engine should not be that hot. Yeah? Make sense? So if you do this one, so I supply 100 joule. Now 70 joule. I used to increase the temperature from 50 to 80, and 30 joule, I use that to push the piston up, 30 joule. Now you see here, I started with 100 joule. Now I still have 70 and 30, 100, right? 100 is equal to 100. Did I destroy the energy? No, I didn't destroy it. I still have 100. But at the beginning, I have the heat energy. After working here, I had 70 joule. Still the heat energy here used to increase the temperature, and 30 joule is used to do the work, that's to push the piston. So 100 is equals to 100. So at the beginning I had 100. So this 100 joule heat is divided into two parts. One is to increase the temperature, another is to push the piston. Does that says the energy remains the same? Yes, it says the energy remains the same, right? I had started with 100 joule at the end of the work. I still have 100 joule. I didn't destroy energy, right? I just changed the form. So this was a heat form. This is a work form. This was a. This is still we call the internal energy, or it's kind of the lost energy kind of thing. Internal energies, yeah. So when we are working and the temperature of the system becomes too high, like this, 50 to 80, this is not good. So if there is a 50 and this is just 60, and I will have a lot of work to push this piston up, maybe 70 here. Okay? So we try to increase that value of work, not value of temperature. So this is the first law of thermodynamics, and there is a homework problem here. So I just give one number, okay, I supply that much heat, that much heat is used to increase the temperature. How much heat is used to push the piston up? Yeah, something like this. Make sense? Good. So I'm in now, there are a couple of things. So I say, so the piston is at this point at the beginning. So let's say I give Q amount of heat here, and then the piston is going to move up like this after absorbing the heat, right? So how do we calculate the work? So I told you we give the work as a dW. So there is an easy way to calculate the value of work. So how much work we did is calculated is like this. Work is equals to, or dW is equals to P dV. This is the equation to calculate the work. So what is P? So how much pressure it is pushing it down here, like from outside, that is the P. So if I am doing this experiment in this room, the atmospheric pressure that is pushing the piston down is the P. Make sense? And what is the volume change? So let's say at the beginning I have here 2 liter. Now at the end I have here 5 liter, right? Now what is the change here? So pressure is, I don't know, the atmospheric pressure, what is pushing this down, that's a P, and then dV is the change in volume, 5 minus 2, 5 minus 2, change in volume. So that's how we calculate the work. Yeah? So it's good. So what is P? The P is whatever it is pushing this piston down from outside, that is the P. So if I'm doing this experiment in room temperature, and let's say this piston doesn't have any weight, that P, the atmospheric pressure, would be this P value, and then how much volume I change from 2 liter to 5 liters. So that much work I did. P multiplied by change in volume. P 5 minus 2 is 3. Make sense? Good. So here is a real problem. So let's do that problem. So everything is same here. So this is saying I have 1.5 liter at the beginning. I have 1.5 liter of gas there, and I expand and it becomes 2.18 liter. And the atmospheric pressure. What is the pressure it is pushing this piston down? Atmospheric pressure. 1 atmospheric pressure. So P is 1 atmospheric pressure. So 1 atmospheric pressure is equals to, we need to do the conversion here. 1 multiply 10 to the power 5 Newton per meter square. So 1 atmospheric pressure is that much in Newton per meter square. Yeah. So that's the unit. So now you can calculate the work. So how much work happened going from this state to this state? So work is equals to P dV. So P is already here. This number put it here. dV is 2.18 minus 1.5, put it there, and convert those in cubic meter. So this one is Newton in meter square, but this is in liter. So this is in liter. So this one, put that number here, 1 10 to the power 5 Newton per meter square. Now dV is 2.18 minus 1.5. 2.18 minus 1.5, but this is in liter. This is in liter. You see, this is in liter, this is in meter. So the liter should be converted to cubic meter. So there is a conversion factor. 1 cubic meter equals to 1000 liters. So convert this liter into meter and just multiply, and you get the answer into. Make sense? So this liter cannot be here. This liter must be converted to cubic meter. So 1000 liter equals to 1 cubic meter. This is a conversion factor. 1000 cubic meter. 1000 cubic meter is equals to, 1000 liter is equals to 1 cubic meter. So whatever this number comes, you can just convert that liter to this liter per 2 cubic meter and multiply. Or you can do the conversion at the beginning. So you subtract 2.18 minus 1.5, whatever the number comes here is a liter, and you multiply by you need a meter cube. You don't need a liter, so put 1000 liter down here and cubic meter part here, and then get this number and put that number here and multiply, and you get the work done. So I did it there, and you can look at that, gives you minus 68. So here is one thing. So if gas expands, if the piston goes up from here, let's say if the piston goes up like this, we give this number as a P negative. Yeah, make sense? But if gas is being compressed, so let's say piston is at the beginning here, so I give the work negative sign here. If the piston is like this, and then let's say you push this piston down here like this, piston push it down, right? You push it down and the volume decreases. At that condition, we give the plus here. So if you are expanding the gas, the piston is moving up, and if you are calculating the work, give it a negative sign. If you are pushing the piston down and the volume is decreasing, and you are calculating the work, give it a positive sign. So we cannot give positive, we cannot give negative for both directions. So it's a kind of, you are going to east one time, another time we are going to the west. So if you give the east positive sign, give the west the negative sign. So if you are moving the piston up, give the negative sign. If the pushing the piston down, give the positive sign. So some book do the opposite way, some book do this way. So our book is always doing, if you are moving this piston up during the process, they give the negative sign. Our book does that way. But some book do the other way. So it's just how they think. So if you give one sign for one way, give another sign, then opposite sign for another way. Make sense? Good. And then, so everything is already there, so you can calculate. So when you calculate the dq, du, then just use that formula. dq is equals to du plus dw. So, yeah, the thermodynamics. This chapter taking a long time for us, so. Here. Okay, I still have 10-minute time. Now, a couple of things here. So, let's say you have this gas here, and you supply some heat here, Q amount of heat supply, right? And our formula is dq is equals to du plus dw. Two things must happen. When you put some amount of heat here, this piston should move up and the temperature of the system should change, right? Two things should happen, right? What happens? You heat it, but this piston does not move. Piston did not move. So this term is 0. So dq is equals to du. So you have a gas and you are heating, the piston did not move. Right? Piston did not move, meaning that there is no work. When piston does not move, meaning that it does not work. So dw is 0. So in that case, all heat absorbed goes to change the temperature. This is the temperature term. All heat absorbed goes to change the temperature. Yeah. Now, what happened here? So let's do another. So let's say this is the thing here, and then you heat it, you heat it here, and then the piston move up, but the temperature did not change. In that case, what happens? dq is equals to du plus dw. So the piston move up, this is not 0, but the temperature did not change, so this is 0. So dq equals to 1 dw. What happened here? All heat absorbed by the system to expand goes to the work because temperature did not change. Make sense? So du is related to the change in temperature, dw is related to the move up of the piston. Yeah? Good. This is important. So I wrote those things there, you can read yourself later. Now, so I give you a couple of examples here. State function. So what is state function? State function. State function. State function. So what is state function? So state function is like this. So let's say you have a 2-liter volume here. This is a 2-liter. Now you can do very slowly. Push a little bit up, a little bit up, a little bit up. You can take 1 day, 2 days, 5 days to do the expanding this gas from 2-liter to, let's say, 6-liter. So what you did is, at the beginning of 2-liter, and you started to put a little bit, and now final volume is 6-liter. So what is the volume change here? 4-liter, right? Make sense? So the volume change here, so if you can write the dV, the volume change is equal to 6 minus 2, so 4-liter. So you really did very slowly pulling up that piston up, right? Now you could do this way, another way. So here is a 2-liter, and then you suddenly, so you just go there and pull it suddenly up within 1 second. You can do that too, right? So still, so we did the very slowly. We did really slowly. Very slowly we did this work, and this expansion of the gas, and the volume change is 6 minus 2-liter. Very slowly we did this. Now you could just do fast within 1 second from 2-liter to 6-liter, and still the volume would be 4-liter. So no matter how you do this process, the volume change is always the same, right? Make sense? Take the cylinder. It's just if you work in a hospital, you have a syringe, right? So if you put the syringe very fast to give the injection to the patient, or you slowly put that medicine, is the same thing. Yeah. So that's called the state function. Yeah. So value not change. How However you do, whether you do fast or you do slow, it doesn't matter. However you do, the value still remains, the change remains still the same. So this is called state function. This is the volume. So most of the time, volume, temperature. So how about the temperature? Let's say I'm working with the volume here. So the volume is state function. Volume is state function. Why? Its value does not change whether I do expansion one way or the other way, slowly or fast, right? The volume change still 4 liter. Make sense? How about the temperature change? So let's say I have a thermometer here. At the beginning, I have a 25 degrees centigrade. So this is 25 degrees centigrade. Now you can heat this gas slowly, very slowly, and you can reach to, let's say, 100 degrees centigrade here. So let's say 100 degrees centigrade here. 100 degrees centigrade. What is the temperature change here? 100 minus 25. This is 75 degrees centigrade is the change in temperature, right? Make sense? I'm really heating the, I have water here or the gas here, and it's a 25 degrees centigrade, and I am heating this very slowly. And at the beginning I was 25, at the end I have 100 degrees centigrade. The temperature changes 100 minus 25 is 75 degrees centigrade, right? Now I can heat this another way. So I don't heat very slowly here. It's a 25. I can just put in the very high heat oven, and it immediately within a couple of minutes it changes to 100 degrees centigrade. What is the temperature change? 100 minus 25 is still a 75. So no matter whether I heat the water one way or the other way, the change in temperature is still the same, right? So this kind of thing is called state function. It's like, so some students come here to study and they also pass. Some students don't come here in the class, they take the online and they still pass. So the initial and final is same, so all pass, right? So state function, no matter whether you come and pass the exam or you stay home and read and pass the exam, it's the same thing. It just depends on the initial and the final state, right? At the beginning, you come to the class, that's your initial state. At the end, you pass the class, that's your final state. What is the difference? Pass minus the initial, right? When you come here, you didn't have chemistry knowledge, but at the end of the class, you pass. So just the initial and final is the same. Pass, right? But how about the learning? So some students who come here may learn a lot. Some students who take online class may learn a little bit. Some students who don't take class at all, they may not learn that much, right? So that's not a state function. Make sense? So the knowledge, the amount of knowledge you take is not a state function, but pass or fail is a state function, right? Just like that. So what is what is not a state function in our case? So let's say not state function. Not state function. So volume and temperature, I told you state function. Doesn't matter how you do this work. Now let's talk about the not state function, the work. So work is not state function, not state function. State function. Work is not state function. So let's say you have some gas here. So it's a 1 liter. Now you expand this gas very slowly. Very slowly, maybe 5 days. It takes 5 days, go from 1 liter to 6 liter, and you calculate the work. So you did a lot of work. If you do the car, drive the car, and you do the car very slowly, your fuel will last many days, right? But if you accelerate your car very fast, all fuel is gone, right? For example, if you drive the American car, they just consume a lot of, they don't give many mileage, right? But if you drive the Japanese car, maybe they give longer mileage, right? With the 1 liter car, maybe you can drive the Japanese car with 1 liter more mileage than the American car. So American car use a lot of fuel. Make sense? So it's just like this. So work is not a state function. So if you do work very slowly, you get a lot of value of the work if you do slowly. But if you do very fast, you don't get that much work. So work is a not state function. Yeah. So it's just like if I walk slowly, I don't want that much heat, right? So I become more. I take the weight, right? But if I run very fast, what happens? My body burns too much fat, right? So I do the different amount of I lost different amount of the heat, right? So if I go from here to that one, I don't burn that much energy, right? But if if I run from there to here to there very fast, I burn a lot of energy, right? So that energy or that kind of work is a state function. If you do one way, it has one value. If you do another way, you have another value. Make sense? I think we learned a lot. So next class, I plan to finish this thermodynamics. Thank you very much, everyone.